Our next keynote speaker is Dr. Christopher Brownell. He joins us from Fresno Pacific University. He is also the author of the book Math Recess, which you received at the registration table this morning. Chris will share a variety of stories that show the deep connection between math and humanity. Thank you so much, Chris.
Hi, thanks, Carolyn. I appreciate it. It's tough being the guy who follows lunch, I tell you. So before I get started, let me just tell you a couple things about me while people are kind of wondering. Yes, my name is Chris. Call me Chris, Dr. Chris, Chris Brownell, whatever. I started teaching as a high school math teacher back in the 80s. There was a time where the years started with 19. And I was a teacher then. And I am now at Fresno Pacific University, and I wrote this book called Math Recess, Playful Learning in an Age of Disruption. And I wrote it with a good friend, Sunil Singh, who lives in Toronto, Canada. And go Raptors. I guess they won or something. Yeah, it's probably not a good thing to talk about the people who beat Golden State, who play right up the street or something. Is that football? I really don't know. Yeah, feel free to keep eating, and that's fine. I am just really passionate about this idea that we teach children about mathematics, and we teach them that mathematics is something that they do. It's something that comes from them. The idea that math is something that exists outside of humanity that we then try to pour into children is really false. But it's a pervasive idea. And the book tries to get at that. And one of the pieces of the book is a section we call storytelling. And I'd like to tell you a couple stories. But before we do that, I'd like to do a couple of things. First, I'd like you all to take a pledge. Would that be all right? We are to be, true math teachers. Okay, so I want you to hold up pi fingers. Pi fingers. Hold them over your heart and say, I promise, to always lead children to believe that they are mathematical, whether they be male, female, or any other, or anything they might desire to become, these people are mathematical. And so am I. The last part's really critical. If you don't think you're mathematical, I'm here to tell you I'd like you to change that. So, now that you are a member of the mathematics club, you have to learn the most important thing, and that's the International Math Salute. Okay? You ready? You're gonna have, is it okay if I take off my coat? Sure. All right, okay. I'm gonna take off my coat. Don't let me forget that thank you. Okay. I think they brought me in after lunch because I'm sort of the comic. So you need to get your, Shalik, where are you? Shalik? Okay, she was here earlier. She reminded me to make sure you have space. So you're gonna need a little space. You need your hands out here. Okay, put them in front of you. Palm to palm, no clapping. Did I say clap? Just right here. Okay, now right over left. Hands together. Wiggle your thumb. Wiggle your little fingers. Wiggle your middle fingers. Wiggle your thumbs again. Got it? Now when you're ready, just come on back. You ready? What? Did I hear do it again? Yeah. Did I hear do it again? Oh, never give me that command. Okay, you ready to see it again? Okay, hands in front of you. Palms facing palms. Right over left. Hands together. Wiggle your right thumb. Wiggle your left thumb. Wiggle your middle fingers. Your little fingers. And your thumbs again. And when you're ready, just come on back. This is the International Math Salute. Why would it be the math salute? Because you're using your fingers, because that's where math starts, on your fingers, yes? For some people. Why else? Why would I ask you to do this as a math salute? Yes? It requires attention to detail and problem solving is her answer. Does anybody agree with her? What's the international sign for yes, I agree? Yes, that's the sign language. Yes. Okay. Any other thoughts on why is this a math idea? Yes.
Because I already think I'm stupid at math, and now you proved it.
No. Just moments ago, you took an oath. You swore on pi fingers that I too am mathematical. I saw you. She said she was not mathematical. This is not about that. This is about problem solving. Right? You paid attention to some details. I think you know the trick. She's shaking her head, yes, for those of you who don't see her. She saw something. Am I a magician? No. I'm a mathematician. I have a PhD in math education, not magic. I can't do sleight of hand at all. I just did something you didn't see. Right?
Yep.
It's sort of a mystery. That's not your, that's what I'm supposed to do. I'm trying to deceive you. Right? You want to see it again? Mm-hmm. Too bad, not going to show you. You thought I would. But here's what I'd like you to do. Where do you want to end up? Put your hands in the position that you want them to end up. Right? So, a very important problem-solving technique is the idea of starting at the answer and working backwards. So start with the answer and then work backwards. Okay, we're not going to do that anymore now. Let's move on. So, before we begin, we need to do the math salute. Okay. You did that. So, my question for you is, where does mathematics come from? And that's rhetorical. You don't have to answer. Although, well, what I'd like you to do is take 10 seconds, think to yourself, where does mathematics come from? Don't speak. Lean to a partner and say what you thought. Have a 15-second conversation about where does mathematics come from. Okay, that has more than 15 seconds. How many people said a textbook? Good, I'm so glad. Very few of you said a textbook. Are you waving that it did come from a textbook? Oh, just. Where does mathematics come from? Did anybody have an answer? Numbers? A need? Nature. Nature. It's a very interesting question. Very interesting answers as well. Where does mathematics come from? I'm not going to answer it for you. So, are we as people, as humanity, discoverers or maker-uppers of mathematics? Maker-uppers, discoverers. Does it exist outside of us? Wow. Very interesting. Very interesting. So there's an article came out in the 60s by a guy, a man, his name is Wigner, W-I-G-E-N-E-R. I can't remember his first name, but he titled the book, The Unreasonable Success of Mathematics in the Physical Science. And his point was, there's no reason for mathematics to work as well as it does. We make it up as we go, was his perspective. It doesn't exist outside of us. We make it up. That's his point of view. So, I'd like to start off by telling you a couple stories. So we're going to start way back. How many of you have heard of Pythagoras? Pythagoras. Okay, so very good. Pythagoras was a Greek. About 4th century BCE. No, maybe 5th century BCE. And he was one of the first people to put together a school of demonstrative mathematics. And by demonstrative, I mean mathematics that actually tried to have a logical basis, to demonstrate connections from fact to fact. And he created this school. And the people who came to the school were separated into two categories. There were the acoustici and the mathematici. The acoustici could only listen to the master. They sat outside the tent. They were the neophytes. They had to work hard to learn by hearing. And the mathematici were the upper grade students who were allowed in with the master to watch him work while he did all of his mathematics on a sand table with rocks and sticks and strings. Most people are familiar with Pythagoras because of his relationship to that triangle-y thing up there. Right? The triangles being the yellow square plus the blue square. If you add up the squares, it adds up to the same number of red squares, right? So long as the, well, it's supposed to be a different color, but blue triangle is of a specific variety, otherwise known as a right triangle, right? The Pythagorean theorem, sometimes people call it a squared plus b squared equals c squared. It's a Pythagorean relationship. Here's an interesting thing. Relationally, we think of it historically, Pythagoras thought of it just like that, as actual areas of squares and a triangle, side lengths of a triangle. Today, we talk about it in terms of a squared plus b squared equals c squared, and we often ignore the connection to the triangle and are more focused on the algebra, right? We've come a long ways from Pythagoras, but there's a lot of very interesting connections there. Pythagoras was a bit of a quack. He was a cult leader, too. The people who were in his cult had to swear, welcome, fealty to mathematics. They believed many strange things, like you should never eat beans. You should never poke a fire with an iron rod. They had all sorts of dress characteristics that were required. Only certain people were allowed to see things. Only certain people were allowed to know things. Yet we give him a lot of credit, right? Pythagoras. Does anybody know how old the relationship that we call the Pythagorean relationship is? Or were you aware that Pythagoras didn't discover it? That it predates him by more than 1,500 years? The Babylonians, there are Babylonian tablets at least 1,500 years older than Pythagoras that have this relationship. And this crazy, wacky guy, though, somehow gets all the credit. It's the way we wacky guys are sometimes. We don't pay too much. They also believed that all numbers could be fractions or were fractions of some kind. Even 9 and 16 and 25 are fractions of another number. They were so committed to this idea that when they discovered that if you tried to make a right triangle out of half of a square cut on a diagonal, can you picture that? My acoustici? Can you see it? A square, cut it into a right triangle, throw away half of the triangle, look at the length of that long hypotenuse. Might be interesting to know that there is no fractional piece of any number that is that length. That number is an infinite decimal with no repetition. It's not a fraction of anything. It's what mathematicians call an irrational number. Irrational because it can't be formed into a ratio. When the Pythagoreans discovered that there were numbers that were irrational, they swore everybody to secrecy. Guess what? I won't make that happen to you. It was enough to swear fealty to mathematics on pi fingers. They were so enamored with that idea and so uptight about it, in fact, that one guy, one of their school, told somebody outside the school that it didn't actually exist, and he went on a long and mysterious boat journey, never to return. He was tossed over by his former fellow cult mates. So the Pythagoreans, and Pythagoras was kind of a crazy guy. Mathematics is made up by interesting people. Right? Made up. We'll move on. Another guy, a little bit later. Have you ever heard of Archimedes? Archimedes, wow, you can see it over here better. He was also a Greek, but he lived much later. He lived on the island we now call Sicily, where Syracuse, the original city of Syracuse, is. He worked both in math and science. He's considered by many to be one of the greatest mathematical minds of all time. All time. He worked in problems having to do with counting the number of grains of sand or estimating the number of grains of sand that it would take to fill the universe. He came up with really great ideas around that. He also invented things in science. He was one of the first people to discover the relationship between what's known as mechanical advantage in pulleys. Have you ever seen pulleys? He created a system by which he could use a set of pulleys and by himself pull a large ship into dry dock by himself. It's an interesting guy. He is so committed, though, to his ideas that this picture down here, the true story of Eureka, the king came to him and asked him about his crown, and he wanted to know if his crown had been faked. He'd given a goldsmith a certain amount of gold to turn into a crown, and he said, when he got it back, he was afraid that the goldsmith had snagged some stuff in the gold and turned it into his pocket instead of into the crown. And the king asked Archimedes, could you tell me if all the gold is really here? But don't destroy the crown. So Archimedes was like, well, I don't know how to solve that problem. Right? I don't know. So he did like lots of mathy people do, like all of us do when we have a problem. We think on it a while. And we go and we take a bath. Right? Anybody ever take a bath to solve a problem? You're mathematical. Guess what? You're mathematical. Right? I am mathematical. You and Archimedes, very much the same. While he's in the tub, he gets a great idea. Such a great idea. He literally leaps out of the tub, running through Syracuse, butt naked, shouting, "Eureka! I found it!" And today we have a principle known as the Archimedean principle of buoyancy in physics, which states how the relationship between water displacement, the amount of water that's displaced by an object, is proportional to the weight of the object, not the volume of it, which is really interesting, was very important to how Archimedes solved the problem for the king. Archimedes also gave us one of the earliest and best estimates for pi. You remember? He gave us one of the best estimates of pi through a sequence of calculations that used a previously unknown technique. Well, kind of unknown technique, sort of called exhaustion, mutual exhaustion. And I won't go into it. If you want to know more, you're welcome to come take my geometry class. I'll tell you all about it. But he was so crazy and so persistent and perseverant. Anybody else ever persevere or fixate on something? He was so fixated on a problem that he died. He literally was killed because he was so committed to solving one problem. The scene up at the top is depicting Archimedes' death. He was fixed on a problem when his city was overrun by the Romans. And the soldiers had been told by the king, by the emperor, bring me Archimedes, but not dead. I want him alive. Bring me Archimedes. Archimedes was working on a problem. The soldier kept saying, come with me. No, the emperor, come with me. Once you come with me, now. No, come now. Come now. Come. End of Archimedes. Also the end of the soldier. Because Archimedes was a genius. And the emperor wanted him. Wanted to know. Wanted to sit with him. It's crazy. He's a mathematician. Okay. Oops, pushed the wrong button. So, from the book, though, we tell a couple of other stories. One important story is we quote a young man. He's a present-day mathematician. His name is Junaid Mubin. And Junaid is very influential in my thinking about this. He says this: mathematics without history is soulless. If you don't tell the story of the mathematics that you teach and where it comes from and what its history is, you lose something really important about mathematics. that it's yours, that it's ours. Good friend of mine, I'm sorry about the YouTube little thing in the middle of that picture. I just took the screenshot and I didn't even think about it. But this is James Tanton. James Tanton is a wonderful guy. He's a mathematician. He's alive today. We tell a little bit of his story in Math Recess. You can read it. It's in chapter 6, James Tanton, an ode to experts or something. He's a well-schooled mathematician. He's from Australia. I used to record a podcast, and I invited James on the podcast to ask him his Genesis story. How did you become a mathematician? Why? What started it for you? And he tells in the podcast of how he grew up in a room with a tiled ceiling. And he said there were 5 tiles square in his ceiling. And when he was just idly staring at the ceiling in his bedroom, he asked himself a question. If I start in the corner tile and move to any other tile that tile is touching, can I visit every tile in that square? And what if I start in a different square? And what if I start in a different square? And it's just idle play, right? This is the kind of thing that a child would do when they're what? Bored. Boredom is not bad. Boredom's a really good thing. It's critical. It's the place where good thoughts can fester. So he's thinking on this, looking at the ceiling. Can you think about that? If you have some paper there and a pencil, draw a 5x5 square and take 2 minutes, put an X in a corner. And then you're going to move from that corner square anywhere you want. Can you go and visit every other square without visiting a square twice? I just draw. It doesn't have to be perfect. Just a sketch. Back of the envelope. Five by 5. Did anybody find a way from starting in this corner? 5 squares. You have to go to a neighboring square. Always go to a neighboring square. Can you visit every square? I'm sorry. Will you stand up and say that really loud?
Can't you just start and go across and down, across and down, across and down, across and down?
Oh, did I ask a real easy question? Sometimes you do, right? Sometimes it's like, oh, it's an easy question, right? Just cross and down and cross and down and cross. Can you visit all 25 squares doing that? Yes. Why did he ask such an easy question? How is that a genesis for a mathematician? Oh, it's an easy question. Because what did he do next? He said, what if I move over a square from this? So what if I don't start in a corner, but start next to a corner? Try that. What do you think? What do you think? For those of you watching online, you should see people. They're staring off into space. They're drawing things like this. Some are drawing, busy. What are you doing at home? I hope you're doing this at home. Ooh, gummy bears. Awesome. What did you think? Yes? No? Yes? Okay. Wow, I asked 2 easy questions in a row. Can there be any real mathematics in this? I must have made a mistake. Let's move on. So, Could I have made a mistake? So James used this problem, and I guarantee you there's a problem here. I've not given it all to you. So the mathematical part of you is going to be left, you can start on the drive home or something. Just play with it a little. Is that okay? Play with that square. So, by the way, what might be your next choice? Yeah. Hey, just forget it. So James decided to become a mathematician. James grew up in, like I said, in Australia, right? He lived way a long ways away from here. And decided to become a mathematician. Got his PhD in mathematics, was a university professor at Princeton, at the Institute of Advanced Studies, kind of Princeton University. He was no shirk mathematician, right? Studied in algebra, if I remember right. James, correct me if I'm wrong. He then decided that he just loved teaching, and he wanted to teach kids. He went into high school to teach high school mathematics because, I love math. And he came across an idea in the high school mathematics curriculum. Now, for those of you, if it's been a while since you were in high school math, or if you never taught high school math, there's a thing called division. And sometimes we divide polynomials, which are really just a fancy way of talking about all numbers, right? Or a particular variety of numbers. And he was looking at it, and he was trying to figure out why does it matter? What's important about this? How do I teach this very abstract idea? It's a very literally abstract idea. You ask the question, if I have a polynomial like x squared plus 7x plus 6, let's make it 2x squared plus 7x plus 6. And I'd like to divide it by x plus 12. X plus 2. Make it simple. What does it matter? Why? How could I ever explain that in a really good way to kids? And he thought, and he thought, and he thought. James is one of the most uplifting and joyful people you will ever meet. Me, I'm a grump. James, he's like, whoa! You cannot come out of a conversation with James without feeling like you've just been like noonied on by one of the most joyful human beings you'll ever meet. He's super happy to see you. Not like me, I'm a grump. But he got super excited about this mathematics, and he started to apply his thinking to it. And in the process, he developed this method called exploding dots. And if you want to hear more about exploding dots, this is a plug. I'm doing a session on exploding dots twice right after this. And it's not for high school. It starts with very early elementary ideas. It's a subject that starts at the root core of what it means to represent a number and builds to a thing that research mathematicians can use. So he invented this. And he was so excited about it, he decided to tell the world. And he began a movement that we now call the Global Math Project. The Global Math Project, its purpose, its raison d'etre, or however you say that. I'm sorry if you speak French and I just butchered your language. Its reason for being is to put in the hands of everyone, as many as will listen, joyful and uplifting mathematics. And so far, in 2 years, we've reached now I think we're over 5.5 million students have registered and worked with this idea of exploding dots. If you'd like, you are more than encouraged to join us. Go to explodingdots.org or theglobalmathproject.org and register your kids. Go through some lessons and teach yourself. Spend 15 minutes learning about not the Global Math Project, but how to use exploding dots. Don't do it now. I'm not done. Learn a little bit about it. Learn a little bit how it will help you help your child or all your children to grow in mathematics, in their ability and their confidence and their sense of joy with mathematics. Okay. So in this book, right after I tell the story, a more eloquently told version of what I just told you about James, I talk about this person, Marjorie Rice. Have you ever heard of Marjorie Rice? No. Okay. I'm not surprised. Marjorie Rice is not a mathematician. Marjorie Rice is not with us any longer, but she's had a profound effect. So let me tell you a little bit of her. Marjorie grew up in the mid-century, 19th century, mid-century, post-war, went to high school in the track of schooling that girls were funneled into, right? You're going into the secretarial pool. She took one general education mathematics class in her secondary education. That general education mathematics, general math, taught her a little bit about fractions, decimals, percentages, very little about shape, geometry, or logical reasoning. Very little of the joy of doing mathematics. Sound familiar? Marjorie, though, was not an unhappy soul. She met the love of her life in her 50s, became mother of several children, raised them through the 60s and 70s. Her husband was an engineer, was always thinking about engineering things. She and her husband decided to get a subscription to a magazine called Scientific American. Are you familiar with Scientific American? Okay, Scientific American, for those of you who aren't, is a periodical. It comes out periodically, I guess. Captain Obvious. In that periodical, there was a column every issue written by a man named Martin Gardner. Martin Gardner is a story I'd love to tell you. I'd love to tell. There's a parenthetical about him in the book, but he's fascinating man. Journalist, not a mathematician. Just absolutely fascinating man. Probably the most important math figure of the 20th century. Not a mathematician. Read the book. You all have it, by the way. Anyway, Marjorie and her husband buy their son, a budding scientist, a subscription to Scientific American. And when the kids are gone and Marjorie's at home, I picture it this way. It's like, I was a young man, and there were magazines you snuck off to read for the articles. And I picture Marjorie when the house is quiet. All the kids are at school. Her husband's at work, all by herself. She flips open Scientific American, flips it into Mathematical Recreations by Martin Gardner, and faithfully reads it every month. And then, in 1970, Gardner put out one article in which he declared that somebody had proven that there were that they had found all of the possible tessellations, which is a tiling based on a five-sided figure, a pentagon. Somebody said, I've found them all. This is all of them. Yay, me! And Gardner's like, yes, yay, you! 6 months later, somebody said, no! I found two more! And Marjorie's like, whoa. So wait a second. I thought math was always right. And then, sometimes it's not. Why? Oh, because it's made up by people. Right? That's not always right. So Marjorie looks at this with no schooling, no idea how to attack this problem, but her own training in organization. Right? And she begins a process in quiet, working on her own. She has no formal mathematical notation. She makes up one for herself. She discovers 3 more varieties of pentagons that can tessellate. So not only was the first guy wrong, but the second guy was wrong. And they were great mathematicians. They were people with letters after their name, like me. And here Marjorie, she bravely writes it down. And she sends it to Gardner. And he says, I don't get it. I don't understand you. These guys say, yeah. But I can't make head nor tails of what you've written here. I can't understand it. So he sends it out to his teams of mathematicians all over the continental United States. He sends it out. They all write back, this looks like the ramblings of a hack. And they dismiss it. Dismiss it. Dismiss it. Except for one woman at Macalester University, Doris Schatzschneider, the hero of this story. Sorry, the heroine of this story. Doris gives it time. And she looks at it, and she digs into it. And she says, I don't understand this notation she's made. I don't understand it. I cannot get it, but I'm going to stick with it. I'm going to, like Archimedes, perseverate on this because I think there's something here. And she cracks the code. She starts communicating snail mail with Marjorie from across the country. Macalister's in Minnesota. Marjorie lives in San Diego. It's 1970. It costs an arm and a leg to make a phone call, let alone, there's no such thing as texting yet, right? You don't email your ideas. It's weeks back and forth. They start a correspondence. Doris is able to prove that Marjorie's found more tessellations of a pentagon than anybody else has. More. And that begins a lifelong friendship between two women in support of each other. Doris helps her refine the work and inspires her. And today, you can look up and find Marjorie Rice tilings. Marjorie starts to discover that these tessellations are beautiful. They're beautiful tilings. And if you've seen an M.C. Escher picture with that's a tessellation, right? That's tessellation art. Marjorie starts turning her pentagons into art. And that artistic side comes out. And she starts to work on that and create those. And then she decides to turn her mind off of the pentagons that look like houses, right? All with this nice, pretty shape. And think about the pentagons that might have a dent in them. Those are sometimes called concave or non-convex pentagons. And she finds 100 non-convex pentagons that will tessellate the plane, that will tile. Now, you don't need to know what that means, but you just need to know, you see, the magnitude of that is phenomenal. 100 of pentagons. And she did it all through meticulous work. Meticulous and painstaking work. Perseverance. Not just perseverance, but perseverance. Sometimes I'm not sure much difference between those two. They send, early in the process, they send her findings back to Gardner and Doris says, Marjorie's right. And that's about 1972 that they do that. It's 1980 before Gardner ever publishes it. Don't shake it. He's not the evil guy here. He's not terrible. He does publish it. But it took too long. There's no two ways about it. But he puts it out, and the world of mathematics is kind of taken by storm. There are now serious mathematicians, schooled mathematicians who are taking up this problem. And they are looking at it carefully. And through the next couple of decades, they become quite persuaded by it. And, forget it. In the book, there's a picture, I cannot recall the page, but it's at the end of the chapter 6, of a tile pattern that's named the Marjorie Rice tile pattern. And it is a picture, it's a picture I took that's in front of the Museum of the Technical Museum in Stockholm. I went there last year just to take a picture of it. No, I went there for another thing, but I did take this picture. You'll see it in the book. She created it. It's hers. When the Mathematical Association of America, by the way, that is the organization that employs James Tanton. Thank you, page 136 in the book. The Mathematical Association of America opened a new building in the late 90s. They were looking for a tile pattern to put down on their foyer. And they were thinking about putting a thing called a Penrose tile after Roger Penrose, a very famous mathematician, mathematical economist. And Doris persuaded the MAA to instead use Marjorie's tile pattern. And they did. And then, here's the best part. A little bit later, several years later, Doris is called to the joint mathematical meetings, which is the premier math event Happens in every January. All of the big math folks, all the big math organizations in North America and around the world come together to the joint mathematical meetings. Literally thousands of mathematicians in one place. Yes, it's that nerdy. And it's great. But she stands up in front of the gathered folk and tells the story that I'm telling you, but tells it better because she lived it. And then says, I'd like to introduce to you Marjorie, who's been doing all of this quietly. Her husband kind of knows she's got this pen pal for 30 years. And they happen to both be at this meeting. And Doris asked Marjorie to stand up, and a room of 3,000 mathematicians erupts in a standing ovation for this woman who went through secretarial school, never learned any mathematics, but changed the face of mathematics forever in a field. Folks, you work with Marjorie. You work with James. You may work with Pythagoras. Hopefully, steer him away from the cult. Right? You touched these people. And you touched the people who touched these people. You have such an important job, such an important role. I want to tell, this story. Francis Su is a mathematician, works at Harvey Mudd College, probably the premier math college in the United States. Do I have just 2 minutes? Okay, maybe I won't tell the story because it's too long. But you should know, Francis was approached by this 19-year-old Christopher. Christopher is incarcerated for the next 17 years. Christopher writes to Francis, who's the president of the Mathematical Association of America, and says, "Can you help me understand math? I always was good at it, but I just was terrible at school. I got in trouble with gangs, and I ended up in jail. But I really love mathematics. Can you help me?" And Francis and Christopher have become great friends. And Francis writes in his departing address to the Mathematical Association as he's leaving, talks to the gathered mathematicians of the association and says, mathematics is about human flourishing. How do we help humans to grow? How do we help them to become greater than the generation before? Through mathematics. So, please, every single one of those children, every single one of those teachers is mathematical, just like you. Thank you very much.